All right, greetings and welcome, friends. Mr. Waddy here. We're talking about 8.4 proportionality theorems, specifically within triangles today. We've just finished talking about triangle similarity and a variety of different ways that we've done that. We had some students toying around in Geometer's Sketchpad, and at least in a general sense, getting a feeling for these theorems. They're not proven yet, but we'll talk about proofs maybe tomorrow. Maybe tomorrow. And so here we go. It says Theorem 8.6, Triangle Proportionality Theorem. If a line is parallel to one side of a triangle, okay, so these two are parallel, and it intersects the other two sides, then it divides the two sides proportionally. Okay, so what it's saying is that RT to TQ, all right, which is actually, the short side, that's right, is going to be similar to RU and US, right? That those are proportional to one another. Now, in terms of a quick proof of that, because of these parallel sides, you would have been able to say those two angles were congruent. Why are those two angles congruent? Corresponding angles theorem, right? And for the same reason, we would have been able to show this, and then we would have had this inside triangle is going to be similar to the outside triangle by angle, but that would only have actually proven that this entire distance was proportional to the RT, and then, you know, using segment addition postulate, you'd be able to get the rest of the way. So that would be your kind of general outline there that you would end up seeing. And then it turns out the converse of the triangle proportionality theorem also works. That if you have a line that divides two sides of a triangle proportionally, all right, so the starting information has just been flipped, then it is parallel, all right? That segment would be parallel to the third side. So those work both forwards and conversely. So there we go. You guys got that. So let's see. Let's take a look at example 1. And it says finding the length of a segment. In the diagram, they've given us two parallel segments. And it says RS is 4, ST is 6, QU is 9. It says find the length, or what is the length of RQ. So could someone give me a proportion, right, using this triangle proportionality theorem, that would help us solve for x? So 6 is to 9 as 4 is to x. All right, so this is to that as that is. Okay, I agree. I agree. Does someone have another proportion that they could set up? Because there's like a lot of different ways we could do this. Four over 6 is to x over 9. That's the one that I would have spotted right away, right? I would have kind of looked at it like that and that. But yeah, there's a lot of different ways to do it. As long as you're comparing like parts to like parts, you can set it up. And then, as always, we can end up solving these using cross multiplication, which, notice, actually, the cross multiplication of this proportion and this proportion ends up being the same, right? If I cross multiply, I'd get 6x equals 36, and over here I'd get 6x equals 36. Divide both sides by 6, and we get x equals 6. They didn't ask us for what x was. In fact, I just made up x, so I guess we should probably write it in the terms that they were hoping for. RQ is going to equal 6. And that's the same thing I would get either way. A bunch of different ways you can set up those proportions, and it's not too shabby. How about this one? Let's see, a shoe rack. A real-life shoe rack problem. Interesting. All right, here we go. All right. It says on the shoe rack shown, B to A, let's see, I'll write this in a darker color, is 33 centimeters. C to B is 27 centimeters. CD is 44, and it says DE is 25. then it says, explain why the shelf is not parallel to the floor. So the shelf is made up of this BD, right, edge there, that segment. There's the shelf, and the floor, we're assuming, is, right, AE is resting on the floor. So really, this is boiling down to prove that these two segments, AE and BD, are non-parallel. How could I prove that? What would I do? How would I set that up? See, Jack, you already put your calculator down. I'm guessing you already tried it out. Did you? Or I don't know if that was what you were calculating, but... Oh, okay. It does. I mean, you could tag team someone else. I was just didn't know if you were... Okay. Well, actually, I realize why you want to do that. But then, like, even just that initial, like, gut check of, wait a minute, there's no way the numerator of this one could be larger than the denominator of that one. So, like, even without trying to reduce those fractions, you could just realize this fraction's less than 1, this fraction's greater than 1. The answer is no, and the reason it's no was what? The converse of the triangle proportionality theorem, right? Since those sides were not proportional to each other, those segments are definitely not parallel, right? Seems to make sense? Good. Let's keep rolling here. Right, today's lesson, not that bad, I don't think. Not that bad. So, all right, we did not experiment with this one in Sketchpad today, but this is what it suggests, that if 3 parallel lines intersect 2 transversals, then they divide the transversals proportionally. Now, my basic explanation of this as to why it would work, imagine if I continued this line and I was artistic. You could imagine that these 2 transversals, when they are non-parallel, would intersect, and then I'd actually have the triangle proportionality theorem applying in those situations. And so you could kind of view just like bigger and bigger triangles being made up of those. So it just kind of, it feels like it makes sense. And then it also works if those are parallel lines, because it is possible that L and M could have been parallel to each other. And it'll actually work either way. So for this, right, the idea is once again that, so U to W is to WY as VX is to XZ. There's proportionality that is at play. And so our example, looks like we've got Main Street and South Main Street. All right, you guys already got that written down. All right, so using the 3 parallel lines theorem, it says in the diagram, angle 1, angle 2, and angle 3 are all congruent. All right, they already labeled those for me. Good. GF is 120 yards. Okay, those are all labeled. DE is 150, and CD is 300. Find the distance HF between those streets. HF, between Main Street and South Main Street. Now, I do not know any parallelness of these lines, but what are you thinking? I saw your hand go up. Aha, okay, so these 2 lines are parallel because of corresponding angles converse. Those are in corresponding positions. And these 2 lines are parallel by corresponding angles converse. And then, like, transitivity of parallelness sounds about right, right? So all 3 of those are parallel to one another. So what I could do is, using the 3 parallel lines theorem, I could find the length of GH here. But notice that isn't actually what they're asking me. All right, they actually want this whole distance, but my theorem is only going to help me set this up. Although maybe you actually could think about this in a different way. So let's find GH first. So GH is to what as what is to what? What are we thinking? What could I compare GH to? proportionally. FG, all right, I'll do it this way. There's more than one way to do it. You could have also compared it to DC. And then if this is the ratio that I started with, then there's only one way. I'm locked in for this next ratio. What would that be? 300 over 150. All right, so I'm comparing this and that and this and that, right? So let's reduce that. 300 over 150 I can actually reduce pretty swiftly. That's just 2. And then I'll just multiply both sides by 120. You could use cross multiplication. You could have reduced and then used cross multiplication. Right, whatever way you like to solve, as long as you're obeying the laws of math, we'll get to the same answer either way. So I get GH is equal to 240, and then just using segment addition, I would say that HF is going to equal 240 plus 120. So HF is going to be 360, and that is not degrees, that is in yards. There is another way you could have set this up. I want to point out, if I wanted to, I could have used proportionality of the entire sides, and I could have actually added 150 and 300 together. I could have actually said HF is to 120 as 300. I'll actually even write that out. I'll take it even slower here. 300 plus 150 is to 150. This also would have worked. I just want to point that out. So you could actually set it up depending on whichever dimension you're looking for. You could have done that multiple ways. All right, last theorem for today. The last theorem. Let's see. We're doing good for time. Nice. Okay. If a ray bisects an angle of a triangle, all right, so you get a triangle, angle bisector, done. Then it divides the opposite side into segments, all right, I believe it, whose lengths are proportional to the lengths of the other two sides, all right? So an angle bisector hits one side, and the other two sides are going to be the AC and the BC here. And what it's saying is that this, all right, and this will be proportional to this and that. Now, we did some exploration in Geometer Sketchpad. We asked the question whether or not these two little mini triangles are similar to each other. And they are not in the majority of cases, because this would have been angle side side. And I'm not even going to write the acronym for that on the screen. That does not work for congruence. It does not work for similarity. All right? It is possible, however, someone noticed that if we moved point C so that the angle bisector happens to be a perpendicular bisector, then you would have two congruent triangles, and the outside triangle would be isosceles. But here we go. This is interesting that even though these two triangles are not similar, two of their sides are still proportional to one another. So let's take a look at example 4. And here we go. Here we go. Whoop, 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 whoop. A yoink with the screen capture. So, it says, using triangle angle bisector theorem, let's see, used to find the length of RS. Ooh, I like this. This is tricky. Notice they gave you a total length across. So don't be fooled, friends. So it says angle QPR is congruent to angle RPS. What could you tell me about PR? PR is what with respect to that angle? PR is an angle bisector, and what would your reason be for concluding that? The two angles are congruent, and does anyone know what the official geometric reason would be? I mean, like, I agree, like, we all know what you're talking about. It's one of the simple ones. It's when it's just definition. Yeah, definition of angle bisector, right. So because that's an angle bisector, then the triangle angle bisector theorem applies. And QR and this x dimension are going to be proportional to those other two sides. Now, they gave me the entire length across. I can't do my dangerous trick of comparing entire side. It's not going to work. So let's just find QR first. All right, so QR is to 7. And there's more than one way you could have set this up. As x is to 13. Right? So this part to that is the same as x is to 13. Now, I'm actually not going to be able to solve for x or QR. I've got two unknowns. Could someone give me another fact that might help us out here, though? Okay, 15 minus x equals QR. 100% agree. If you didn't recognize that, you might recognize it in this form. QR plus x is equal to 15. And why is that true? Segment addition postulate. Yeah. And watch this. If I solve for QR here, I'll get QR equals 15 minus x. And then I can do some substituting. I was going to do like a curly bracket. Yeah, that's pretty good. And I'll plug this in for QR all the way over here. So 2 equations, 2 unknowns. Back to the days of Algebra 1. Lovely. Just like so comfortable, like you're getting home, changing in your PJs. Back in the days of Algebra 1. Wow, so great. Aren't you guys happy to be back? So to solve this, now I've got 1 equation and 1 unknown. Cross multiply is probably what you guys are fans of. I can't add x to both sides because this one's locked inside the numerator. If I multiply both sides by 7, then I could add x to both sides. But I'll do the cross multiplication here. So 13 times 15 minus x is equal to 7x. Let's see, where's my slider here? Rip, rip, rip. And now I could distribute and solve. But yeah, so I can't access that x when it's inside of a numerator. That fraction bar is a type of grouping symbol. And the fraction bar, by the way, is called a vinculum, which my wife shot down as a name for one of our sons. I don't know why. Vinculum would have been a great name. Vinculum Waddy? Been awesome. Let's see. So now what do I do to solve for x? Let's wrap this up. Doesn't look like it's going to go in evenly. That's okay. I mean, fractions do exist. Divide both sides by 20, and I'm going to end up with x equals... What'd you end up getting, Anthony? 9.75. Cool, cool. All right, now I'm somewhat suspicious because it was a decimal. The book agreed with our work, though. I just checked it. All right, well, thank you so much for watching, Internet friends. We're going to do some construction here in a minute, so have a good day. Bye-bye.